Okay, let's unpack this. We've all heard the incredible claims about AI models lately, right?
Oh, yeah. Models that seem to not just give answers, but actually show their work.
Exactly. They generate these detailed, step-by-step processes that, well, they look suspiciously like thinking. Super impressive sounding.
It absolutely feels that way sometimes, definitely, just based on the output.
Hmm.
These models are often called large reasoning models, or LRMs. They're basically a special kind of AI language model.
Specialize how?
Well, they're designed specifically to tackle complex problems by generating these detailed thinking processes before they give you the final answer.
Got it. So, for this deep dive, we're really taking a hard look under the hood using a fascinating bit of research.
Yeah, this paper from Apple, it's called The Illusion of Thinking, Understanding the Strengths and Limitations of Reasoning Models via the Lens of Problem Complexity. Quite a title.
It is, and it really signals their approach, doesn't it? They take a really clever, uh, quite rigorous angle here.
They really do. Instead of just using the standard tests, which might have
What the
problems.
model already saw the answers somewhere.
Exactly. Data contamination. Or the tests just don't show you how the model got there. This paper uses tests where they can analyze precisely how these models try to solve problems.
Especially as those problems get harder and harder.
Precisely, as complexity increases.
So our mission today is to unpack what they found. Are these models truly reasoning, like in a robust, general way?
Or is there maybe something more like an illusion going on, as the title hints, especially when things get tricky?
Right, so get ready for some insights that might genuinely change how you think about what these, well, thinking machines can and can't actually do.
It's definitely true that recent LRMs, the ones people talk about like OpenAI's o1, o3, DeepSeek R1, Claude 3.7, Sonnet Thinking, Gemini Thinking,
Yeah, the big name.
they have shown big improvements on some tasks. And a key reason is they generate these thinking processes, chain of thought, sometimes called, or just traces.
And that's definitely fueled a lot of the excitement, I think. But these researchers, they kind of pump the brakes a bit, right? They question the standard tests, math problems, coding.
They do. They argue those tests aren't really getting to the, let's say, the heart of reasoning ability.
Why not? What's the main issue?
Well, a couple things. One, as you said, is data contamination. The models might have just memorized answers or patterns from their training data.
Okay.
And two, standard tests often just score the final answer, pass or fail. You don't get enough insight into the actual step-by-step process, the reasoning trace, to see why it worked, or, maybe more importantly, why it failed.
So you can't diagnose the thinking itself.
Exactly. So they decided to, well, build a better mousetrap. They came up with controllable puzzle environments.
Ah, puzzles. Okay, that sounds clever. Why are puzzles better for this?
Well, think about it. With a puzzle, you can precisely control the complexity. Just add more disks, more checkers,
Well, you can dial it up systematically.
Exactly. And you avoid contamination because you can generate endless unique puzzle instances from simple rules. They haven't seen that specific puzzle before.
Makes sense.
Plus, puzzles demand algorithmic reasoning based only on the rules you give them. They can't just rely on stuff they read online. They have to figure out the logic.
Okay.
And maybe the biggest advantage, because the rules are formal, you can use a simulator to check every single step the model generates in its thinking.
Not just the final answer, but the whole chain of thought.
Every single link in the chain, it's like getting a perfect X-ray of the model's attempt. Super rigorous evaluation.
That ability to check every step feels huge.
Yeah.
So what puzzles did they use? Anything familiar?
Yeah, classics. Things like the Tower of Hanoi, moving those discs around.
Yeah, I remember that one.
Checker jumping, swapping pieces on a line, river crossing puzzles.
Where you have to get people across without leaving the wrong ones together.
That's the one.
Yeah.
And blocks world, stacking blocks in a certain order.
Okay, so different kinds of logical challenges.
Right.
And they just made them harder by adding more pieces.
Exactly. More disks, more checkers, more pairs for the river, more blocks. They often call this complexity factor N in the paper.
Got it. So they got these great puzzle setups. Now they pit the thinking models against the regular ones. What happens?
Right. This is where it gets really, really interesting and maybe a bit sobering compared to the hype.
How so?
They compared the LRMs, the ones generating thoughts, like Claude 3.7, Sonnet Thinking, DeepSeek R1, with standard models that have similar computing power but don't do the explicit thinking step.
Okay, a fair fight computationally.
Yep. Across all these puzzles at different n values, different complexities. And what emerged was three distinct patterns, three regimes of performance based on complexity.
3 regimes. Okay, what's the first one?
Regime one, Low complexity. Simple problems. And here's the first surprise. The standard, non-thinking models often did better,
Better. Without thinking.
or at least just as well. And they used fewer resources, fewer tokens. It seems like generating a long thought process for an easy problem is just overkill, inefficient.
Huh. So thinking too much can actually hurt performance when it's simple.
Apparently so, for these models anyway. It's not what you'd intuitively expect, right?
Not at all. Okay, so that's low complexity. What about the middle ground, regime 2?
Regime 2, medium complexity. Now, this is where the LRMs, the thinking models, really start to pull ahead.
Okay, so the thinking step helps here.
Absolutely. The advantage of breaking the problem down, attempting that step-by-step reasoning, becomes clear. The performance gap widens. The thinking models are definitely better when the problem is, moderately challenging.
So there is a sweet spot where generating the thought process provides a real benefit.
Seems like it. That's where they shine.
But what happens when you keep cranking up the difficulty? What about regime 3, high complexity?
Yeah, this is the big one. Arguably the most significant finding. When the problems got really complex across all the different puzzles,
What happened?
both types of models, the thinking ones and the non-thinking ones, just collapsed. Complete accuracy collapsed. Performance often dropped straight to zero.
0. Not just worse, but completely failing.
Completely failing. The paper shows graphs where it just tanks. Now, the thinking models might delay that collapse slightly. They might push the boundary a tiny bit further.
But they still hit the wall.
They still hit the wall hard. They don't overcome this fundamental limit.
Wow. That collapse is stark. It suggests there's something about scaling complexity that current approaches just can't handle, thinking or not.
It really does seem that way. And it gets even weirder when you look at how much effort they put in as they approach that collapse point.
Effort. How do you measure AI effort?
By the number of thinking tokens they generate, basically how long is the step-by-step thought process they write out.
Okay, so logically, as the problem gets harder, they should generate more tokens, right?
Right.
Try harder. Put in more effort.
That's what makes sense. And initially, they do. As complexity ramps up from low to medium, the thinking token count goes up.
Okay, good.
BUT. And this is the really counterintuitive part. As they get close to that high complexity threshold where accuracy is plummeting towards zero,
Yeah.
their reasoning effort, the number of thinking tokens, starts to decrease.
Decrease. They start thinking less just when the problem is hardest and they're failing. That makes no sense.
It's bizarre, isn't it? They're failing, the problem's tougher than ever, and they generate shorter thought processes.
Are they hitting some kind of length limit? Like they can't generate more?
That's what you might think, but the paper explicitly says no. They checked. The models could generate more tokens, they have the budget available, they just don't.
So why would they decrease effort?
The paper suggests it points to a fundamental scaling limit in their ability to maintain, coherent or useful reasoning as the problem's own complexity explodes.
Yeah,
It's almost like the thinking process itself just breaks down and peters out.
like they just give up.
Yeah.
Or the attempt becomes garbled.
Something like that. It's less like focused effort and more like the mechanism failing right when you need it most. Hitting a cognitive wall and just trailing off.
That finding alone, the decreasing effort when facing failure, feels like a powerful point against it being, true persistent reasoning.
It's definitely puzzling. And because they use those puzzle environments, they could actually look inside the thoughts, those reasoning traces, step by step.
Right, the X-ray vision. What did that show? Did the thoughts look different across the regimes?
They absolutely did. For the simple problems, remember where the standard models sometimes did better?
Yeah, the overthinking regime.
Exactly. The analysis showed the LRMs often found the correct solution quite early in their generated thoughts, but then they'd keep going, exploring incorrect paths after already finding the answer.
So inefficient. They solve it, then confuse themselves.
Pretty much. Now, for medium complexity, where the LRMs performed best, the pattern flipped.
How so?
They tended to explore incorrect solutions first, kind of stumbling around, making mistakes within the thought process. And then the correct solution, if they found it, would often appear much later in the trace.
So it looks more like trial and error, maybe. Exploring, making mistakes, sometimes correcting course within the thought process itself.
Yeah, perhaps like a search process, feeling its way towards an answer. There's some evidence of correction there.
But what about high complexity, where accuracy collapsed to 0?
While the trace analysis just confirmed the collapse, no correct solutions were found, no useful paths. The generated thoughts themselves were just ineffective. The thinking process had completely broken down.
So it seems any ability to self-correct or productively explore is really fragile, only working in that medium zone. Outside that, it's either inefficient overthinking or just total failure.
That seems to be the picture, yeah.
Yeah.
And the study also found a couple of other really surprising limitations, things that, again, make you question if this is general reasoning.
Oh, what else stood out as unexpected?
Well, one huge one was their inability to reliably follow explicit instructions, an algorithm.
Wait, what do you mean?
So the researchers did this experiment with the Tower of Hanoi. Instead of asking the model to figure out how to solve it,
Yeah.
they gave it the step-by-step algorithm, the exact sequence of moves needed. They just asked the model to execute those steps.
Okay, so they basically handed it the cheat sheet, the
Yeah.
perfect plan. Surely that let it solve the harder versions.
You would absolutely think so, but astonishingly, no. Performance did not significantly improve.
Seriously.
Seriously. And that accuracy collapse. It still happened at roughly the same complexity level, even when it was just following instructions, not finding them.
Wow. Okay, that's massive. It's not just that they can't find the solution, they can't even reliably execute it when told exactly what to do if it's complex enough.
That's what this suggests. It points to a potential limitation in precise computation, or like following procedural instructions faithfully, not just a discovery bubble.
If you hand someone the IKEA instructions for a complex build and they still can't manage it, that's a pretty fundamental issue for calling them a reliable builder, isn't it?
It definitely raises deep questions about the nature of their processing. And there was another key finding pointing in a similar direction. Surprising inconsistency across different puzzles.
How so? You mean they were good at one type of puzzle but bad at another?
Exactly. Even when puzzles seemed comparable in complexity or required a similar number of logical steps, the model's performance could vary wildly.
Can you give a specific example they mentioned?
Yeah, they pointed out Claude 3.7 sonnet thinking. For a Tower of Hanoi puzzle with 10 discs, which takes 102 moves total, the model could manage almost 100 correct moves in its trace. Pretty good.
Okay, almost perfect execution on a long sequence.
Right. But then they tested it on a river crossing puzzle with just 3 pairs of people. This puzzle only needs 11 moves total to solve. Much shorter.
This should be easier, right?
You'd think. But the model only managed about 4 correct moves before completely failing.
That is bizarre. Handles nearly 100 complex moves okay, but falls apart after 4 moves on a logically simpler, shorter puzzle.
It makes no sense if you assume a general, consistent reasoning ability that scales predictably with, say, the number of steps required.
So what could explain that?
Well, the paper speculates it might be down to the training data again. Maybe they've seen tons and tons of Tower of Hanoi examples, so they've kind of memorized the pattern or structure.
But river crossing, especially with N3, might be much rarer in the data.
Exactly. So this inconsistency strongly suggests they might be leaning heavily on pattern matching or analogy to specific things they've memorized rather than deploying a general logical toolkit. And that breaks down fast when they hit a problem structure they haven't effectively seen before, even if it's objectively simpler.
Okay, let's tie this all together. We've covered a lot of ground, peeling back the layers on these reasoning models. Let's connect this back to you, the listener. What does all this actually mean?
Yeah, what's the takeaway? I think it fundamentally tells us that these thinking processes, these generated traces, while they're definitely powerful in certain situations, particularly that medium complexity range,
They aren't a magic bullet.
definitely not a silver bullet for achieving true, robust, general-purpose reasoning. Not yet, anyway. Understanding these limits, the collapse at high complexity, the weird decrease in effort, the failure to follow instructions, the inconsistencies, that's crucial.
Crucial for how we think about AI, how we use it, maybe even how we build the next generation.
Absolutely. It means we need to be, well, discerning. When an AI shows its work, yes, it looks impressive. But this research cautions us not to just automatically equate that output with genuine, flexible, human-like reasoning.
It's about digging deeper than the surface appearance of thought. Is the process reliable? Is it generalizable? Or is it brittle?
Precisely. Are we seeing real logical deduction and problem solving from scratch? Or is it more like incredibly sophisticated pattern completion, statistical mimicry that just looks like reasoning within certain boundaries?
Which, yeah, brings us right back to that provocative title, The Illusion of Thinking. Are we maybe being fooled by the surface sophistication, mistaking really advanced pattern matching for genuine flexible thought that can handle true novelty or high complexity?
It's the key question, isn't it? And especially that finding about failing to follow instructions. If you give it the exact algorithm and it still fails on complex cases, what does that really imply about the nature of its thought and process, even when it succeeds on easier stuff?
Is it actually deriving logic, or is it doing something else entirely, something more akin to recalling and adapting patterns?
Right. And it makes you wonder, what fundamental changes are needed? What shifts in AI design or training might get us past these limits, the collapses, the inconsistencies to build AI that can truly reason in a general, reliable way?
Definitely something to mull over as these technologies continue to develop so rapidly.
Indeed, it's a fascinating look at the current state of the art and its limitations.
Well, thank you for joining us for this deep dive into some really thought-provoking research on the limits of large reasoning models.
We hope this gives you a clearer picture of what's going on under the hood and maybe a more informed perspective next time you see an AI claiming to think.